One of the most famous thought experiments in the field of quantum mechanics is Schrödinger's cat. Proposed by Austrian physicist Erwin Schrödinger in 1935, this experiment was designed to illustrate the strange and counterintuitive nature of quantum mechanics. The experiment involves a hypothetical cat that is placed in a sealed box with a vial of poison gas, a radioactive atom, and a Geiger counter. If the radioactive atom decays, the Geiger counter detects the radiation and triggers the release of the poison gas, which kills the cat. However, since radioactive decay is a probabilistic event, it is impossible to predict exactly when the atom will decay. According to the principles of quantum mechanics, the radioactive atom is in a superposition of states, meaning that it exists in multiple states simultaneously until it is observed. This means that until the box is opened and the atom is observed, the cat is both alive and dead in a state of superposition. The experiment is meant to illustrate the concept of quantum superposition, which is a fundamental principle of quantum mechanics. According to this principle, particles can exist in multiple states at once until they are observed or measured, at which point they collapse into a single state. However, Schrödinger's cat also illustrates a paradoxical problem with the interpretation of quantum mechanics known as the measurement problem. If the atom is in a superposition of states, and the cat is both alive and dead until it is observed, then who or what is doing the observing? Does the act of observation collapse the superposition, or is there some other mechanism at work? There are several proposed solutions to the measurement problem, including the many worlds interpretation, which posits that every possible outcome of a quantum event occurs in a parallel universe, and the Copenhagen interpretation, which states that the act of measurement collapses the superposition. Despite its theoretical nature, Schrödinger's cat has found practical applications in the field of quantum computing. In quantum computing, bits of information, known as qubits, can exist in multiple states simultaneously, which allows for exponentially more powerful computations than classical computing. For example, a quantum computer with 4 qubits can perform calculations on all possible combinations of 0 and 1 at the same time, meaning it can perform 2 to the power of 4, or 16, calculations simultaneously. This is why quantum computing has the potential to revolutionize fields such as cryptography and drug discovery. In conclusion, Schrödinger's cat is a thought experiment that illustrates the strange and counterintuitive nature of quantum mechanics, particularly the concept of superposition. While it may seem paradoxical, it has practical applications in the field of quantum computing and continues to be a subject of debate and exploration in the field of quantum mechanics.